I don't know if I ever talked to you about this. We might have talked about it briefly on a previous episode. But you remember quantum superposition and quantum entanglement? Have I ever mentioned those things?
Quantum entanglement we talked about when talking about teleportation. I don't remember quantum superposition.
Okay, so that's a start. Basically, quantum superposition means, or rather what superposition means, is when you have an electron, or not an electron, an atom that has several different states. Like, I don't know if you remember this from chemistry, like high school chemistry, but every atom has several energy states, right? So that those electrons can move between each state. And that, like, one genuine thing I remember from chemistry is that when an electron moves from high energy to low energy state, it releases light. It releases energy. Do you remember any of that stuff?
That sounds vaguely familiar. What's the names of these states? Do you know? Okay.
Do you remember the energy states, like the S, P, D, F, or I think those are orbitals.
Yeah, I think those are like
orbitals.
the
Yes.
the rings of
yes,
the
those
elements.
are orbitals. Yes, so you have like a 1s, you have a 1s state, a 2s, a 3p, 4d.
Yeah, okay,
5F,
yeah,
all those
that's
things,
the
yeah.
elements and their proton
Those are the
rings.
energy states
Okay,
right
yeah,
there.
yeah.
Proton
No,
rings.
that's how it is. Each element has a specific
Yeah,
number
you
of
could say it like that.
protons, and each amount.
Not protons, electrons.
Same difference.
Protons are in the nucleus.
Yeah, but
no.
No, but like protons define the element.
Yeah, but they're present in a nucleus, bro.
Okay, whatever.
Yeah.
Electrons have states and they create light. Okay, got it.
Yes. So, what superposition means is that any electron you can take can be basically what it means, and I can explain this better with Heisenberg's uncertainty principle, and which I will explain literally right after this. Basically, any quantum state can be existing, like it has an equal chance of existing at the same time. So let's say an electron has an equal chance of being in any possible state
at any time.
Yes, at any time, and there's like a certain probability that it is in all those states. So that makes no sense, I know, but it will make more sense once I explain this thing. So Heisenberg's uncertainty principle. Have you ever heard of, or not Heisenberg's? Schrodinger's
cat.
Schrodinger's cat. That's what I meant. I said Heisenberg. I meant Schrodinger.
Jeez,
Please
Louise,
don't
Pete,
don't
how
kill
the
me.
heck do you mix those two up?
Dude, all these theoretical all these physicists from like the early 1900s, they're all the same people, so it's fine.
Okay, yeah, Schrodinger's cat is the famous experiment where you put a cat in a box filled with poison, and until you open the box, it's declared both being alive and dead since you don't know.
Exactly.
Is that a superposition?
Like you don't know. That is basically superposition is derived from that thought experiment.
Having two things simultaneously, hypothetically existing at the same time.
Exactly. Or in the same place at the same time because you don't know where it is. And that's also tied to Heisenberg's uncertainty principle as well. But that's more so what the orientation, while the superposition is position.
Okay.
So, because of that, we can have qubits. These things are called qubits, quantum bits for long, qubits for short, which are basically the same thing, not the same thing as regular bits, but they are the quantum version of bits. So you remember bits from your CS days, right? You know how they work?
Do I know how they work? No. I just know that they're like data or
data,
they're like the value
well, a bit,
the size.
Yeah. So your traditional computer reads information in ones and zeros.
Binary, yeah.
Yes, binary. It's a bit can be either a 0 or a 1. So let's say I wanted to type my name out. My computer has some kind of representation of that using zeros and ones. Let's say I wanted to write the number 4. I can represent that in binary with the number
100.
Yes, exactly.
Okay, Pete.
And that's because you can do a bunch of calculations and stuff. So you know binary. Don't mess around, dude.
I know what binary is. I learned that. I don't know what a bit is, other than it's like related to data and.
Well, a bit is literally each number in a binary sequence.
Okay.
It's either the zero. It can be a 0 or a 1.
Oh, so that's what a bit is.
That's literally a bit.
That's silly. Whatever.
Like you've never heard of 8-bit or 32-bit?
I did. I always thought that just referred to like the amount of storage, like the amount you can store.
Nope.
Like how much you can process at the same time.
That's what it is. Yes.
Okay, yeah.
Yes.
Okay, we got it, Pete. We know bits now. We know superpositions.
Okay, cool. So what a quantum bit, like I said, is a quantum version of a bit. So typically with our regular computers, we have transistors that have logic gates, like transistors that are made of silicon. That's why Silicon Valley has its name, because that was where Intel and all those other superconductor companies, they made all those transistors to make computer chips.
And that's why it's called Silicon Valley?
Yeah, I swear to God.
You learn something new every day.
There you go. Anyways, instead, what we use for processors of quantum computers are these elements that we can take the electron. So, like, for instance, one example would be the outermost electron for the phosphorus element. And we use that as a qubit rather than using transistors with logic gates from the element silicon. We can use the outermost electron from the element phosphorus, use that as a qubit, because what a qubit is it uses superposition of states. So it cannot be a 1 or a 0 deterministically. It can be both a 1 and 0 until we measure what it is.
Okay.
Do you need a second to process that?
Say that.
So
say
basically,
that again?
what I'm saying.
No,
is,
shut up. Say it again.
Basically, what I'm saying is, a qubit can be both a 1 and a 0 at the same time,
and that's
until we measure it. Just like Schrodinger's cat can be dead or alive until we open the box.
And how do you use that for calculation?
Well, that is such an incredible question. Basically, what it does is it allows you to add more and more qubits because we don't know what the actual state of them are. We can give more. It's basically like adding variables to the equation, and then you have to multiply by a constant in order to get a certain probability of an answer. And in order to increase the probability of the desired answer, there is some signal stuff. But that's getting too far. Basically, what I want you to focus on right now is that they can be 1 and 0 at the same time.
Okay, sweet.
Got me?
Yeah, no, I got you. I'm with
Okay.
you, Pete.
So yeah.
Not really.
So back to classical computing. Let's say we have 2 bits of information. We have four distinct possibilities for that, which is really only characterized by 2 numbers. We can have 0, 0, 0, 1, 1, 0, and 1, 1.
Yes.
That's 4 distinct numbers. Now, let's say we had a qubit, which, like I said before, can be a 0 or 1 at the same time. Let's say it could be like 65% chance of being a 0 and then 35% chance of being a 1. You don't know until you measure it. So because of that, like I said before, we need to multiply by a certain constant. You feel me?
Okay. Where do we get this constant? Or what is the constant?
It's just like, I don't know, Greek letters, man.
Cool.
The constant itself doesn't necessarily matter. It's the fact that you have to multiply by a constant.
Okay.
So we have 4 distinct numbers, but only 2 numbers to represent those, right? The 0 and the 1, which are already predetermined, correct?
Yes.
So that's what's really important here. We can get 4 distinct numbers from 2 numbers only, right? But with quantum computers, because you need to multiply by that constant, we had those 4 different pairs. We need to multiply by 4 different constants.
Okay.
Okay? So that means that we need 4 different numbers, 4 different constants to get 4 numbers, or 4 possibilities, 4 possible answers.
Okay.
So because of that, we're able to increase the complexity of the problems that we can solve.
How?
Well, because everything is all still, like I said, it's up in the air until you measure it.
So you can solve 4 problems in the span of one?
Yes, it gets exponentially faster the more bits you add to the equation. So, right, you know how the more bits you add to a classical computer, it's a square function.
Yeah.
So for quantum bits, for qubits, the more bits you add, it's an exponential function. It's 2 to the n.
Ouch. That's gonna get
Yeah.
big really fast.
Exactly. So that means that the more, that is essentially the more quantum bits you have, the more complexity in the calculation, or the more complexity required of your computer. It's also like its best feature is its greatest weakness, or like its greatest strength is its greatest weakness. Because of the added complexity, the more qubits you have, the more hard it is to keep it stable. Because, like these things, they exist in like super, super cold chambers, like cryo chambers close to the 0 Kelvin,
Yeah,
which is like
sub-zero.
negative 270 degrees Celsius plus.
Yeah, this is
Or
to make it
minus.
superconductive so it calculates things really fast.
Exactly. And because of that, they need to keep it extremely unperturbed, really like isolated, or else, like the smallest little change or like anything that can that can alter the state of the machine could screw a calculation completely. Like it needs to be perfect. And that's just by virtue of the tech being not as developed right now.
Okay. So when I build my own supercomputer, a quantum computer, I need to put it in my fridge just to be safe.
Yes, essentially.
Okay. All right, I'm
So,
ready.
yeah. So basically, build yourself one of those, put it in the freezer, and then you can calculate how fast it would take an apple to fly to the moon.
Sweet.
In like less than a second.
One of
No,
life's
so
biggest mysteries.
yeah. So, like I said, the more qubits you add, the more complicated the system becomes, but also the more calculations you can do in a shorter period of time.
Okay.
You understand?
Yeah.
Because like I said, the increase in qubits gives more possibilities, which allows you to have more complex calculations done.